right?
So negative 2x.
What rule are you going to use to take derivative of this?
Chain. Product.
Product, yeah. You had said it earlier. You said product. So, yeah, product. Everyone, we're going to do a product rule right there. So this, again, goes back to the way you learned product rule. I mean, let's just do a quick poll, because I'm going to do it the same way all throughout the semester. Let's say we have two functions, f times g, and we take the derivative using the product rule. I teach my classes to do f prime times g plus g prime times f. That's the way I teach it. In other words, I do derivative of this one times that plus derivative of that one times that. How many of you do it that way? Really? Okay. No one does like this first? Yes, you do this first?
Yeah.
Okay. So if I do it this way, you're going to be okay? Yeah, okay. So just be aware that, you know, it may look a little different than the way you learn it, than the way you learned it. Shay?
Yeah.
Shay? So I want to tell you why I do it this way.
Because it makes sense when you do the quotient.
Quotient, okay, good. All right, perfect. All right, so we're going to use that rule. So James, you want to keep going? We're going to do like f and g here. So we're doing this first.
Just be y squared.
So 1, I'm going to put the 1 even though it's not there. 1, and then y squared is your g. And then plus, I'm running out of room here. And now the derivative of y squared. 2y dy dx. I'm going to use y prime because we were using y prime over here. So times, and then times x. Ooh. Sorry that's smashed in there so much. Okay, there it is. There's our derivative. Now, this is where in Cal 1 you might go solve for y prime, right? Like go solve it for y prime. And that algebraically is going to be a pain in the ass. Would you agree? And the good news about this question is not asking you for y prime. It's asking you for the equation of the tangent line. So all we need is the value of y prime at this point, right? So why don't we just replace x and y with 0 right here, right now, and then solve for y prime. It'll make our lives so much easier. You all understand what I'm saying? There it is. Okay, so now I'm going to say, you know, at the point 0, 0, this equation becomes 1 over the square root of, well, if that's 0 and that's 0, that's gone, right? So it's just 1 minus 0, that's just 1, and root 1 is 1, and 1 over 1 is 1. So that's all just 1, okay? Yeah, I'll just put 1 down here. And then times, let's see what's in this parentheses. Well, that's 0, right? And then these are zeros. It kills, everything's there. Everything is dead, right? So that's 0. And then equals the right side, which is 1 plus y prime, right? So left side becomes just 0 times 1, that's 0, equals 1 plus y prime. And now you can solve for y prime, negative 1. So that means the slope of the tangent line there is negative 1. Are we done? We're not done. This was just our slope, right? That was just this. So now I'm just going to come back to this and plug in 0 here, and negative 1 there, and I'll be done. So y minus 0 equals negative 1 times x minus 0, like that. Clean it up, y equals negative x. There it is. Y equals negative x. That is a line, right? That's the equation of a line. And if I graph it, I should be tangent to that curve at the point 0, 0. Yeah?
Yeah.
I don't think I need to do it. Would you all agree?
Yeah.
That diagonal, negative x, would be the line we're looking for. Okay, so that was just an exercise with some, you know, do you remember how to find equations of tangent lines? Can you do implicit differentiation? You know, when do we actually have to solve for y prime as opposed to just plugging in and getting the value? All right, we can move on. A rocket is fired straight up with at a speed of 1,000 miles per hour. An observer who is a mile away from the launch point is tracking the rocket with binoculars. At the moment the rocket is 3 miles high, how fast is the observer's angle of inclination changing? This look like Cal 1? Related rates, one of your favorite problems? Yes? You love these? Okay, I'll read through it one more time. Rocket, 1,000 miles per hour. Observer, 3 miles away. Okay? 3 miles away. Sorry, no. At the moment, the rocket is 3 miles high. The observer is with binoculars, and the observer was, what, a mile away from the launch point? Let me draw a picture. Okay, I'm going to draw a picture of what's going on here. And yeah, I'll just do it here. So, we have the ground. We're going to assume the Earth is flat for this, okay? Right? We're not going there. So rocket's going straight up like this. Here's my rocket. Saturn V, obviously that's a very good picture of a Saturn V. There's a little man with binoculars, okay? My Cal 1 class knows not to be intimidated by the artistic ability. I've been doing this for a long time. What's that? The shadows? Yeah. I'm going to leave the shadows out. I don't want people to go drop the class when they see how good that is. Okay, so when I'm doing these problems, and again, there's going to be differences in the way you were taught. When I'm doing related rate problems, I always draw a general picture, and I draw another picture that represents the instant in time that we're talking about. Okay, so at the instant we're talking about, I'm just going to use points now, okay? At the instant we're talking about, how high is the rocket? 3 miles. So we can start labeling things. 3 miles, I'm just going to put MI. And how far is this distance from here to here? This is 1 mile. That's not changing, right? Not the 1 mile. And what are we interested in here? The question said, what is the angle of inclination? How fast is that changing, right? So I want to know, like, as this person's watching it with binoculars, how fast is their head rotating, right? At that particular instant. So we are interested in knowing this angle theta and how fast it's changing. Now, if I give you these two sides of a triangle, can you tell me what theta is? You can. You could use, in this case, an arctangent on your calculator to get that angle. I'm going to wait on that, okay? Over here, though, in the general picture, this from here to here is 1, and that doesn't change. Okay, the observer doesn't move. But this right here, the height of the rocket, is changing. So we have to label it with a variable. Can I use h or y? What do you want? Y? Okay, y is changing. And then we also have the angle of inclination, which is theta. That is changing. All right, so those are our two pictures. One of them where things are changing. This is moving. This is not. This is moving. The instant in time, 3 miles high, 1 mile, that is actually fixed now, right? That is a number. We don't know what it is without a calculator, but it's fixed. And then what I like to do is I like to write down what I'm given and what I want. Right? My Cal 1 students, this is the way I taught it, okay? So what are we given? There's some information that's given to us about this rocket.
1,000 miles per hour.
1,000 miles per hour, and that represents what? It's how fast y is changing, right, as that moves up. So we can write that as dy dt. Will we use t? Because t will be like time, right? So dy dt is a rate, it's a speed, and so it's a derivative. It's 1,000 mph. What is it that we want? We want to know how fast theta is changing with respect to time, right? We want that. When do we want it? At what moment do we want that? At the exact moment that the rocket's 3 miles high, so when y is 3. Right? Okay, one volunteer, tell me what the next step would be. One volunteer. Go ahead. Good, you have to get the equation. You have to find an equation that relates what to what? What you're given to what you want. So in other words, some equation that you can come up with from these pictures, is specifically this one, that relates y to theta? Do you have one or no? No? Yeah, I think you do. Just think. Pardon? Okay, Pythagorean would be this squared plus this squared is this squared. We don't have this side, and we're interested in theta. That wouldn't connect these two together. Think trig.
Maybe cosine? Be tangent.
Cosine would be here and here. Tangent would be here and here. Do y'all agree? Tangent of theta is this side over this side. Yeah? So I could write that down. So here's an equation that relates the two. Tangent theta equals y over 1, which is just y. Now once you have that, what do? You differentiate it with respect to time. Okay? So you differentiate this equation with respect to time. So if I do that, let's see. Shay, I called on you or no?
You haven't really called on me, but you're on. I can do this.
Okay, so what would you do at this point?
You'd set d theta over d time for tangent of theta is equal to d y over dt of y, which is 1.
I understand what you're saying, but we would need to say d dt in front of tangent theta. I think that's what you mean. Tell me if I'm wrong. And then d dt of y. Okay, so you're taking derivative with respect to time of this and derivative with respect to time of this, yes? That's all right. Okay, you want to keep going? All right. I'm going to erase this. So what is the derivative of tangent theta with respect to t? It's all right. We can move. Who? I heard someone. Secant squared. Okay, so derivative of tangent theta is secant squared theta. All right, so be careful though. We've got secant squared theta times,
d theta.
yeah, you have to take derivative of theta with respect to time also, so d theta dt. Now we're done with the derivative on the left side. Equals, over here, that's just dy dt. And then we look at this, and this is, okay, this is a critical point right now, because I'm about to make like a bigger point. Right now, are we in business? Can we get the answer? We want to know what d theta dt is, right? Here it is, right? This is what it is. Like, we have a way of solving for it. In order to solve for that, we need to know what dy dt is. Do we know that? Yes, we do. It's 1,000. But we also need to know what? So I'm going to put a check here. We have that. We also need to know what this is, don't we? So we need to know what theta is, or we need to know what secant theta is. But we have some work to do, don't we?
Yes.
Don't we? Okay. What was this section about? 3.5. The inverse trig functions, right? Do you see any inverse trig functions here? You don't, do you? Okay, so let me back up to this step right here. Remember when we were here with that equation? Okay, I'm going to do something that would not be absolute, like it wouldn't be normal for you to do this. But now that you've seen it, you might agree with me. So I'm going to take arctangent on both sides. Right? Okay, what's the left side become? Theta. What's the right side? Arctangent y, right? Go with me? Okay, now differentiate with respect to time. This is still an equation that relates theta and y, isn't it? But now we're involving arctangent instead of tangent. So what is the derivative with respect to time of this side? Just d theta dt. And then the derivative of arctangent of something is what? 1 over 1 plus whatever that argument is, squared, chain rule, times derivative of y, which is dy dt, right? And separate it from this. Do y'all see the difference between this and this? Over here, we had this, we were good, we're solving for this, but we still had work to do. But we do it this way, d theta dt is what we're looking for. It's already isolated. And look what we need to know. dy dt, we have it, and we need to know what y is, and we have it. There's no more work to do. We never had to mess with theta at all. Does y'all see the difference in that? So it's yes, you could get the same answer this way, but it's just more work, right? So it's more efficient to do it this way. All right. The homework assignment, I believe that's correct, but go off of the calendar here. Let me just double check it. We're not done. We still have time. Yeah, that's your homework. I think I don't know, we used to have these rags in here that I think they've taken them away from us. Oh, there is one there? Was it on the floor? They made them black so you can't tell how dirty they are. The old ones were yellow.
How can you be like that?
You got a question for everyone, James, or you're okay?
I was lost for a minute, but I'm
Okay.
I was trying to figure out, I was like,
No, you said you were found.
I'm gonna finish it, okay? I was just trying to figure out, like, how could your angle be 100 if it's looking at that? But I was like, wait, it's not what it's asking.
It's a rate. Yeah, it's a rate of change. And you would have to be careful in that, make sure you're answering either degrees per hour, I think. Everything was miles per hour, right? It was miles per hour. So everything is measured in hours. So it would be degrees per hour or radians per hour. You'd have to make sure you're...
So you would say 100 per hour?
Well, I didn't solve it. When you solve for d theta dt, that will be radians per hour. Then you would have to convert it to degrees per hour. All right, now, the next topic. Show of hands here. Did anybody cover the hyperbolic functions in Cal 1? Yes? Here? You didn't do it. Really? Okay, maybe, yeah, could be. These two sections kind of like instructors decide whether or not they want to do them in Cal 1 or in Cal 2. I always like to do this one in Cal 2 for sure. All right, so the trig functions in Precal, all the trig functions came from, well, there were two basic ideas. You could either draw a right triangle, talk about sine, opposite over hypotenuse, cosine. So you can draw a right triangle and then define all the trig functions. Or you could do a circle and define the trig functions. That's from Precal. Now we're defining these new functions called hyperbolic trig functions. And these 6 new functions have nothing to do with right triangles. Okay? They involve some combination of exponential functions. So this is the notation we use for the hyperbolic sine function. Sin with an h and then of x. The definition of the hyperbolic sine function is you take e to the x, you subtract from it e to the negative x, and you divide the whole thing by 2. So let me try and write that out a different way. This is what the hyperbolic sine function is defined to be. Right? That's its definition. So you're taking an exponential function. What does that exponential function look like if I were to graph it? What does e to the x look like? It goes like this, and then multiplying it by a half just kind of shrinks a little bit. So we have like this function like that, and then what does e to the negative x look like? It's going to flip, so it's this one like this, and then shrunk down. And you're subtracting it, right? You have to be careful. Subtracting means that it is negative, so everything that was positive is negative, so it's actually this function here. You don't worry too much about this, okay? But you've got you're like adding, if you change this to plus and that to minus right there, you're basically taking that function and adding it to this function. So you get some function that's like in between the two. All right, and let me show you the picture of it. Don't worry about the pictures. There it is. Okay, there's your There's your hyperbolic sine function, all right? Now, you might be asking yourself, like, why in the world, like, where did these come from, you know? And it turns out that it's actually backwards. This expression right here turns up a lot in physics and engineering. That expression is there a lot. And so we just said, okay, well, since we're seeing it so much, let's just define it to be a function. All right? So it's kind of backwards than the way we normally do it. It's like this thing just keeps on appearing, so we'll have a name for it. So we have the hyperbolic sine. And then notice for hyperbolic cosine, what's the only difference between these two? That's a plus, that's a minus. Okay, so the sine has the subtraction. The cosine doesn't, all right, has the add. And then what are the other four trig functions? They're just, well, the tangent hyperbolic is just that divided by that. And then the cosecant hyperbolic is just the reciprocal of this one, and so on and so forth. So now we have 6 new trig functions, don't we? 6 new. Yeah, 6 of them. Now, I thought it might be interesting to show you, before we get into messing with these, where these things appear. So I have an experiment that I'm going to do here. See if this turns out good or not. I have my doubts right now. I didn't test this before class. All right. So here's what I'm going to do. I'm going to get this string. And I'm just going to tape it up here. Get this other end. Tape this over here. Right about there. All right. Catenary, that's what this is called. A wire that's suspended between 2 poles forms what we call a catenary. Now, when you look at that, what function does that look like that you've seen in the past? Looks like a parabola, right? Doesn't it? So what I'm going to do is I'm going to sit here and remember all parabolas can be written in this standard form, right? A times x minus h squared plus k. The h and the k give you the vertex, right? And then the a tells you whether or not you open up or down. It kind of narrows it. And so this little program I have allows me to draw parabolas. And I get to control everything. So I'm going to move my vertex up, and I'm going to try and fit a parabola to this. Okay, so maybe I can cheat. It's pretty close, right? What do I need to do maybe? Bring it down a little bit, right? What's going to happen when I bring it down though? Damn, that looks really good actually. It's pretty close, but we're off. We're off in here, aren't we? Okay, well, it turns out there is no way to model a catenary with a parabola. You have to use the hyperbolic cosine function. That is what draws a catenary. So now let me try. Now this is it right here in the top left. Can you all see that? A cosine hyperbolic x over a plus c. I'm going to bring that in, and I'm going to see if I can fit that one in here any better. I'll work on that in a second. Whoa, it moved there. Oops. It's hard to do. Boy, the parabola looks better, doesn't it? The parabola looks better. I have to have these two kind of in the same spot. You have to take, this is a complete like counterexample, it looks like, right? This looks like I proved myself wrong. You have to kind of take it on faith here. I think maybe my scaling on my graph is not right, not 1-to-1, but the only way to do a catenary is to use a cosine hyperbolic function. I'm trying to see if I can. Can y'all take it on faith or not? Yeah. That's better. That's better. So parabolas don't work. So that's just I'm just showing you an application of where you would see it in the real world. Any wire going from one place to another, if you wanted to model that mathematically, you'd use a cosine hyperbolic function. And once you have that, you can calculate anything you want. So like if you wanted to know if this was a pole, right? And you wanted to know the force, okay? Because this is going to be applying a force on whatever's holding that wire. There's a load on that, right? You would want to know the angle of that force, right? Like what direction it's pointed in, which means you need to know the slope of the tangent line in order to figure that out, which means you need to take derivative, which means you need the function, right? So there's different things you could do with that. You can also use like the hyperbolic tangent function is used to calculate how fast a wave moves. Like if you have a wave moving, and like think of like the ocean or something. You have a wave moving across water. You know how deep the water is. You know the height of the wave. Then you can calculate the speed at which it's moving by using a hyperbolic tangent function. So I mean, there's all sorts of applications. I'm just trying to get you to believe that they're useful. All right. But what are we interested in here? We just want to know what their derivatives are, right? We want to know, do they have inverses, right? Maybe they have inverses, and those inverses might have derivatives also. So we have like another whole category of functions to worry about now. Let's see how we're doing. 10 minutes still? 12 minutes? All right. So let me just show you a picture of the hyperbolic trig functions. There's your hyperbolic sine. Here's hyperbolic cosine. Notice those don't look anything alike. Like our standard sine and cosine, they're like pretty close. They're just shifted. Not with the hyperbolics. Tangent hyperbolic. Okay. Cosecant hyperbolic. Secant hyperbolic. Cotangent hyperbolic. That's just too much stuff on one screen. But you don't have to have those memorized or anything. Just wanted to show you how different they are than what we've seen with the regular trig functions. Now, do you remember with your regular trig functions, you have all these identities? Like sine squared x plus cosine squared x equals 1, your standard like Pythagorean identity. This is an identity for hyperbolics. Notice it's not the same, is it? It's cosine hyperbolic squared x minus sine hyperbolic squared x equals 1. Let's prove that identity. Let's prove it, all right? That's what we're going to do. We're going to prove this is true. How do you prove an identity? Start with one side, turn it into the other. So I'm going to start with the left-hand side. What is the definition of cosine hyperbolic x? It's e to the x plus e to the negative x all over 2. That's cosine hyperbolic, right? Squared, right? Squared, minus sine hyperbolic, which is e to the x minus e to the negative x over 2, but then that whole thing is squared. We want to show that that's equal to 1, right? So now let's square. So when we square, I'm going to take my time on this. All right, so I'm just rewriting it, yeah? So just square the top and bottom. And I haven't actually squared this. I'm going to do that on the next step. So let's see. I'm going to try and say this again. No, you have to say it again. Is it
Rifa?
right? Right. The A is messing me up. Right? If the A wasn't there, I could just say Rifa. It would be easier. So I'm just going to put a little mark on the A for my own Rifa. Okay, Rifa. Can you expand out that top? Right here. So what would we get if we multiplied these two together? So what would this in here, what would that give me?
X squared.
E to the x squared? You mean like this? E to the x squared?
No,
Yeah?
X is squared.
Square that x? How about this? If I said x to the m to the n, what do you do with these exponents? Multiply them. You multiply these, right? So this is really x to the m times n. So if we have e to the x squared, we have to multiply these two, which means we'll get 2x, okay? So we're going to have e to the 2x there, and then here, what would we get? You have to, you're adding the, you can add the exponents, right? So e to the plus e to the 0, which will be a 1. And then the middle one, add those exponents, e to the 0 again, and then plus e to the negative 2x, right? Okay, that's our top. And then all over 4. And then the only difference over here is that we got some minuses to worry about, right? And then we have this one here, don't forget that. So we have e to the 2x, and then here minus e to the 0. The middle one, another minus e to the 0. And then the last one, plus e to the negative 2x, and then all over 4. And I think we can start putting everything together. These have the same denominator, don't they? So it's everything over 4. And then this minus sign is going to wind up going through here and making that a minus, making that a plus, making that a plus, and making that a minus, right? So let's put that all together. I'll have e to the 2x, take away e to the 2x, gone. 1, 1, e to the 2x minus e to the 2x, right? Those are gone. So these guys are gone. All you're left with is the e to the zeros. And how many of them do you have? You have 4 of them, right? So you have a 4 up here, and 4 over 4 is 1. So that's an identity. And there's in your homework, there's several other identities that you're asked to go prove, all right? And it's just so you can get used to this algebra, just the algebra in here. It's nothing crazy algebra, but it just kind of gets us thinking again about the way exponents work and these properties. So here are some important identities. We just proved one of them, right? We just proved this one. But there's some other ones that are important. What's that first property?
Sine hyperbola negative x equals
Negative sine hyperbolic x. What is that property called when a function, when plugging a negative into the function is the same as plugging in positive but then changing that answer to negative? We call that function a certain type of function. Odd function. That's an odd function. And then what's that second one? Cosine hyperbolic negative x equals cosine hyperbolic x. We call that an even function. So hyperbolic sine is odd, and hyperbolic cosine is even. And then this one we proved. This one you could prove also, right? But the algebra in here is going to be messy, all right? These are like the sum formulas from Precal. They should look somewhat familiar, but there's little differences in the signs here. We're not going to get into that. You can do that in your homework, prove some of those identities. Really, what we want to establish before we end class here is what are the derivatives of these 6 new trig functions. And there's some good news and bad news. The good news is these look somewhat familiar to the derivatives of your standard trig functions, right? Like derivative of sine of x is cosine x, right? Well, derivative of sine hyperbolic x is cosine hyperbolic x. So that lines up exactly with what we already knew with regular sine, but then things start to change. The derivative of a hyperbolic cosine is hyperbolic sine, not negative hyperbolic sine. How would we prove this?
Can't you use the definition of a derivative?
Like limit?
Like, the definition is f.
Like limit f?
Yeah, the definition of a limit, pretty much. So pretty much
You
the-
could, but I would probably express my condolences as you started the problem because it would be brutal probably. You would use identities. It could be done. Look at this way though. Look at, if we just do e to the x minus e to the negative x over 2, this is what hyperbolic sine is, right? That is? And we just want to take derivative of that. So when I take derivative of this, I can really look at that as being the derivative with respect to x of 1/2 times e to the x minus e to the negative x. In other words, that 2 on the bottom can just come out as a 1/2. And then we take derivative here. Let's do it carefully. When you do derivative, you have a constant in front. It just comes along for the ride. And now let's take derivative of these term by term. So derivative of e to the x is itself. Minus, now be careful here, derivative of e to the negative x is itself, but then times the derivative of what's up here, which is -1. So you're going to wind up getting e to the negative x times -1, and the negative and negative now turn that into a plus. So now you have 1/2 e to the x plus e to the negative x, which is cosine hyperbolic. Isn't that the same as what cosine hyperbolic is? Y'all see that? Put the 2 back on the bottom. Now you're looking at cosine hyperbolic. So derivative of hyperbolic sine is hyperbolic cosine. That shows that's true. And if you do the same thing with cosine hyperbolic, you can show that it's sine hyperbolic. Again, these are things you don't have to prove, but you all need to know these are here, right? 2 minutes. I think that's probably where we're going to stop. Yeah, that'll be a fun place to pick up. Yeah, so as you're packing up, I'll just kind of verbally and do your homework for 3-5. That's your assignment. Oh, and I didn't talk about quizzes. Quizzes can come in any form, on any day, at any time. So next class you walk in, I expect that you did the homework for 3-5. I'm not going to come around and check it because I've provided you all the answers online, right? But I may give you a quiz over that material, all right? Yeah.
So
All right.
is the homework, is that online, like on WebAssign?
No, it's from the textbook. So you're supposed to have the textbook for this class.
Okay.
Now, do you have a WebAssign account? No?
Yes.
You already do? Do you have a book?
I am getting my book.
Okay, well, you can use your ebook.
Okay.
Was it for, well, we have to make sure it's the ebook for this class, though. So if it's not for this class, it won't work.
Okay.
Because if you have the ebook, you could just go open up the ebook and look at the assignments online instead of having a physical book.
Okay.
Yeah?
I think I like the physical book better.
Yeah, you can probably get it pretty cheap nowadays.
Okay.
Yeah. All right. I'll answer more questions if you have them. Let me turn off my camera. Everybody have a good day.